Listen. First topic that I will be talking about, that we should know, Coulomb's law. It is Coulomb's law that is studied as the first topic in electrostatics. Weierstrass's law as the first topic in magnetostatics. Whether we can prove them experimentally straight away or not, we can't prove it in our labs, I'm sure about it. Coulomb's law in electrostatics gives the force on a point charge due to other charge kept at a distance. Knowing the charges, we talk about the force experienced by each charge. Point charges, it is impossible for us to conduct an experiment with point charges and prove that this is correct. Now, everywhere you should know that when something starts developing in science, that particular area in that science will start talking about, first of all, the simplifying assumptions made. From that, the equations are developed, points are developed. At each stage, if it is possible, we will come out with a formula. One stage of research will give us one formula. Can I prove it? Can I prove whether that particular formula is right or not? Depends upon whether I can conduct an experiment to prove that particular formula. I have to conduct an experiment to get the quantity given by that particular formula, taking the different quantities specified in that formula. Conduct an experiment, determine the quantity, use the formula, obtain the quantity by using the mathematical calculation. If at any stage I can experimentally verify the value that I have calculated by using the formula, that formula is correct. There are so many formulae which are just given in the initial stages, cannot be straight away proved. We basically take such things. Ultimately, at some higher level, we prove it. So these assumptions are made. One formula is derived based on that. Somebody takes that formula as the reference, cites that particular formula in his research, and then they develops one more formula at the higher level. They come nearer to the practice. No? When they come nearer to the practice, somewhere they will come to a stage where they can conduct an experiment and verify the correctness of that particular formula. At the stage where an experiment can be conducted to verify that the correctness of that formula, if they don't match, and you have conducted the experiment properly and you have calculated it using proper units, still if they don't match, you will come back to the root. Hey, these assumptions are not correct. And then go back. And you know all these things. Actually, you know from the beginning, this is what we did. Atomic model. Somebody started with plum-pudding model. Then nuclear model. Then Bohr's atomic model. Nuclear model come because of, everybody was thinking that actually plum-pudding model is correct. Oh, this is what. And then Rutherford, by chance, conducted an experiment called as alpha particle scattering experiment. He bombarded golden 5. We really wonder why this fellow had done it. But still, large angle deviations in alpha particles told that there is positive charge concentrated inside the atoms, because of which they told nuclear model of atom. Then electrons are there. It is electrically neutral. How these electrons are there? They will be revolving around, somebody told. Rutherford's model. Then hydrogen spectrum they saw. And then they told not all orbits are possible. That's what, no? That's how they basically say. Some experiment comes that will give you some information. So go back and then change the atomic model. Now check whether this particular phenomena can be explained because of that. That's how in stages science develops like that. Force on a point charge. I will not really much worry about what Coulomb's law is. But still, we basically in Coulomb's, I will take it as a mathematical input to me. I will not worry about whether that is correct or not. I will just consider that it is correct because somebody gave it. Definitely, Coulomb's law gives me the force on a point charge due to other charge. Then I will immediately define electric field intensity because of a point charge at a given point. It's like this. You know that there is something called as gravitational force of attraction between two masses. Earth is a huge mass. If you leave an object in air, it goes onto the Earth's surface, comes down because of the force of attraction. Definitely, that force of attraction, you know, is directly proportional to the mass of the object. And we call the force acting on any object as its weight. At a particular point, if you give m1, its weight is m1g, it's m2, m2g. What we basically characterize the field as with is what? The gravitational field is characterized by giving acceleration due to gravity, which is the weight of unit mass of object kept at that particular point. In the same way, I will characterize the electric field by giving the electric field intensity at any point because of a point charge. Giving this electric field intensity as the by notation. The force experienced by a small positive test charge per unit of the charge. Having known the electric field intensity at any point in the field of, in the region of influence of a point charge, I will use integration, single, double, triple, to determine the field at any point because of a line charge, because of a surface charge, because of a volume charge, by dividing line into so many points, differential line elements, by dividing the given surface into so many points, each point being a differential surface element, by dividing the volume into so many points, each point being a differential volume. I will know how to use the formula that gives the field at a point because of a point source to determine the field at any point because of a distributed source, which is either line distributed on a line or surface or in a wall. Even in Biot-Savart's law, we straight away, not as a force, field intensity, field due to point source, current element. Again, it's a point. Ultimately, current element is what? A small, infinitesimally small line. Line is what? Cylinder of zero radius. Filamentary current, we call it. The current element, whenever we talk about also, I should know that this current element is filamentary. No current is filamentary for us because it's a conductor of finite dimensions or a surface of finite dimensions we'll have. Nowhere I will be able to see filamentary current because I cannot have a conductor of tending to zero radius. And that current, I will first of all know the field at any point because of the Bard-Savart law. Somebody gave it to me. Ultimately to be verified. Ultimately, these are verified to be correct later on, because of which I will say that I will take it. I will try to reason it out why different terms are there in that, but still I will know this to explain it. Having seen this, again we will see there is a current carrying conductor, distributed current, single current, single integral, double integral. Maybe there are places where you have to use double and triple integral also. Thick conductor, line current, filamentary current, we will not have, of course. But sheet currents are there, surface. Normal thick conductor through which everywhere current is there, it's principally to be taken as the triple integral of the effect at a point because of that particular one. Using integration, knowing the effect or knowing the field quantity because of a point source, I will use integration to determine the field quantity because of the distributed source. I will be trained for that. In fact, when we talk about the field, for me, one that creates field is antenna. Even in the chapters practical. No, this is where it is practice. Ultimately, you can see, you can measure its pattern. You can say this is how its pattern will be. You will say by using the subject, and then you can measure it. When we go to antenna as a topic, this antenna is always considered to be the combination of infinitely many Hedge-on dipoles. That's also a current element, carrying, of course, a sinusoidal current. Sinusoidal current. Because what we transmit by using antennas is always a modulated signal. Low pass signal, when we speak, it is audio signal converted into electrical signal, will never be given as the input to the antenna because the antenna height required will be in kilometers. Unpracticable. Impracticable, rather. I will always, whenever I want to use free space of the channel, I want to use antenna, I will go to the radio frequency spectrum. Radio frequency is what? Radio frequency is one that can be converted into electromagnetic wave by using a realizable antenna. No antenna is a point. But the first thing that we study in antennas and wave propagation as a topic is Hedge-on dipole. It's the propagation radiation characteristics. Then every antenna radiation characteristics are obtained by using integration of that particular quantity, depending upon the way in which the antenna is there. I will use this knowledge of determining the field quantity because of a distributed source, knowing the field quantity because of the point source. I'll become expert initially itself, and then I will use my knowledge in the practical cases, right? This is the first thing that we will be looking at in electrostatics and magnetostatics. Then distributed sources, fields. Next. Yeah. Electric field intensity only is determined by using this. Once you know the electric field intensity, like if you know the acceleration due to gravity at a particular point, if you keep a mass here, mg will be its weight. Mg will be the force of attraction towards the center of the earth. Like that, electric field intensity is defined as a force and a unit positive charge, mathematically speaking. In a Q charge, you get QA will be the force on that particular charge. Because it is basically defined with respect to positive charge. If it is positive charge, the force will be in the direction of the field. If it is negative charge, it will be there in the direction opposite to the field. Now listen carefully. Now listen. Initially, we basically do this, take the Coulomb's law, feel it because of a point source, and then integrate it to determine the field quantities of a set of standard charge configurations. Next, the most important thing is, again, this cannot be proved. I cannot see it. We will introduce displacement flux. Now we talk about luminous flux, which we cannot see. What I can see is light source and the illuminator object. What goes from the source to the object is flux. And the flux goes and eliminates the object, because of which I will be able to see. In the same way, we define something called as displacement flux here. And here also it is magnetic flux. Things are same only. Flux, then flux density, then relation between flux density D, relation between D and E. If I know D, I can calculate E at that particular point in the medium. Listen carefully. It's purely imaginary thing. I will take this. I will use this concept to determine the field quantities of the objects that I have already determined using integration. I will develop a procedure. Using that particular procedure, we will determine the field quantities of some sources. And those sources, no, basically the volume sources and all, are such that it's impossible, even if you are an expert in mathematics, mathematically it becomes really impossible for you to determine the field quantity using integration. In such cases, we use the concept of displacement flux to determine the electric field intensity and then measure it and say correct also. At higher level, this is proved. And while talking about this flux density, please see this now. We speak about a particular thing called as divergence. If at all anybody can understand divergence properly through subject, it is only the people who study electromagnetics and learn divergence through electromagnetics. Divergence of a vector field. This divergence is there in the calculus part of vector calculus part of our maths. If you want to learn, people know, they intelligently remove this electrostatics, because anyway you have to study divergence. You have to come back through electrostatics only if you are properly learning it. After divergence, we speak about divergence theorem, Gauss divergence theorem, right? And this Gauss divergence theorem if you can properly use, it gives a lot of mathematical advantage to us. You are supposed to evaluate, let us say, the surface integral of a quantity over a closed surface. In any coordinate system, a regular closed surface consists of, in space, 6 surfaces. X is equal to x1, x is equal to x2, y is equal to y1, y is equal to y2, z is equal to z1, z is equal to z2 is the closed surface. Rho 1, rho 2, phi 1, phi 2, z1, z2 in the cylindrical coordinates. R1, R2, theta 1, theta 2, phi 1, phi 2 in spherical coordinates. Whenever I want to evaluate the surface integral of a particular function over a closed surface, we should know that we have to evaluate 6 double integrals. Really tedious mathematically. And there is every possibility that the sign convention is confusing and you will go wrong also. Because it's monotonous for us. For surface 1 it is there, for surface 2 it is. When it becomes monotonous, normally human beings get irritated, because of which the efficiency of doing that particular quantity will come down. Divergence theorem really gives you a clue. And only if you know something called as charge density, volume charge density, the relation between the volume charge density and the field quantity, you will be able to understand divergence theorem there. Instead of evaluating the surface integral of a vector quantity over a closed surface, 6 double integrals. You take the divergence of which it is differentiation. Take the volume integral of which one triple integral. A differentiation operation followed by triple integral is equivalent to evaluating 6 double intervals. Definitely the second one is advantage in many cases. We will understand through that particular displacement flux. Ultimately, I will tell you the applications of the Gauss law also. There are tremendous applications in our subject also. And there are places where your mathematical methods fail. And it becomes extremely important for you to determine the field quantity there. The best example is actually parallel plate capacitor, cylindrical capacitor. Practical, no. Mathematically speaking about spherical capacitor. Cylindrical capacitor you take. Even though you are a giant in mathematics, right? Using cylindrical coordinate systems, if a finite cylinder is there, it becomes impossible for you to determine the field quantity inside the field cylinders. Gauss law to be used. Now, you want to understand capacitor through this subject. This is what is the subject topic that I use. Divergence and Gauss divergence theorem. Next, in this. These are all vector quantities. I have defined the vector field quantity by defining a vector flux density vector at a point, every point. Electric field intensity vector at every point. When I want to integrate a vector quantity, component-wise I have some integrated. Otherwise, integration blindly adds. It misleads us in so many places also. I'll tell you, it tries to cheat us outrightly. Whenever I want to determine the vector quantity because of a distributed charge. For x component, one integral is to be used because all x components can be added. All y components can be added. All z components can be added because they are in the same direction. Because of which any integration of a vector is equivalent to 3 integrals. One integral for each component. Instead, if I can define and completely describe that particular field by using a scalar quantity, it's a wonderful thing for us. And the scalar quantity that we basically define and I use everywhere in my circuits is voltage potential. I will understand what potential is. What potential at a point is because of a point charge. If I know the expression for the potential at a point because of a point charge, it is just integration for me to determine the potential because of any distributed charge. Potential being a scalar quantity, integral is a single scalar integral. Definitely, when I am trying to basically describe a field, the best way of describing the field is giving the potential at every point. That's why somebody who is studying antennas know that magnetic vector potential is the starting point of antennas. It is not the field quantity. Later on, we use the potential and determine the field quantities. That's where it is important for me. I will talk about voltage, potential in the fields, potential difference to be understood for network analysis, right? I know any source, voltage source of EMF creates the potential difference between the terminals. Potential and potential difference I will understand. I will try to calculate the potential difference through potential difference between the conductors. I will use the potential difference V and the charge Q to talk about the first component called as capacitor. Complete. I will derive the expression for the capacitance of a capacitor as a function of its dimensions and the medium used. And I will see what is the formula that I have to use if it is a parallel plate capacitor, normally this capacitor that we use in lab. Or the cylindrical capacitor, which is the electrolytic capacitor that we use, as well as any coaxial cable is a cylindrical capacitor. For the sake of talking about the capacitance of a coaxial cable, I know the calculation, I should know the way in which capacitance is defined and the capacitance of a given capacitor is calculated. I should derive the formula for that. And somebody gives you the dimensions and medium, immediately calculate this is the capacitance. And this capacitance calculation between the conductors, a bit higher level if I want to go. People really struggle a lot here. Many people sit together, do the job of spice monkeys, and then spice monkeys what? Trial and error. Millions of trial and error operations they do and ultimately fix the component values, not by using design formula. They develop an IC like that. When they develop an IC like that, different components are to be interconnected through a layout. When they go into layout, ultimately the chip manufacturer, the fab fellow, will extract the capacitance and give, hey, these are the capacitances that are there, inter-electrode capacitance, inter-track capacitance. All those capacitance, if you want to understand, a VLSI designer ultimately should have enormous knowledge of this capacitor, inter-electrode capacitances and the positive and negative aspects of. There are so many places where capacitance is positive. There are so many other places where capacitance between the terminal becomes nearly killing aspect. It has a negative effect. We need to understand this capacitance thoroughly from the beginning. I will do it. We will do it through electromagnetics. This potential difference will take us to capacitor. After this, I know the scalar quantity V at any point. At any point in the field, there is V, there is E. There should be a way to calculate E from V. V can be calculated easily by using scalar integral, because of which the first field quantity that I calculate is V. From V, if I want to calculate the electric field intensity at any point, because somewhere I want to know the force. Somewhere I want to know the force. Mathematics, there is a topic called as gradient of potential. This gradient of potential, gradient as a topic. That's why I tell you, right? We are really blessed with subject. Mathematics people will never understand what gradient is. I'm telling you, we will understand gradient properly and completely. And this gradient of potential, potential is a scalar quantity, gradient of potential is a vector quantity. V is connected to E through gradient of potential. This will basically talk about, in mathematics, there is a topic called as directional derivative. There is a surface, they will say, I want to integrate the normal component of a particular vector quantity at each and every point. There is a surface defined mathematically. To talk about the normal component of a vector field at each and every point on the surface, I need to know the normal direction. Unit vector in the direction perpendicular to the surface at each and every point in a general surface. If you understand gradient of potential, definitely you will understand what directional derivative is and determine in mathematical advantage of looking at the potential. We normally develop the potential difference through electric field, but ultimately, when I want to calculate all the field quantities, first thing that I will do is potential. Then I will use the gradient of potential, calculate the electric field intensity. Using electric field intensity, I will determine the force, but in the course of time, I will say force, field intensity, potential difference. But when I want to calculate potential to, that's what I will go back. And I will understand the mathematical topic called as potential gradient, having studied potential and potential difference. This is what is the point now. When I talk about potential difference and the charge that is creating this particular potential difference in a system of conductors, I would have spoken about capacitance of that particular system of conductors. I would have developed this directional derivative. I know what gradient is. Using divergence and gradient, please look at it. We develop something called as Poisson's equation. See the way in which the syllabus is interlinked for us. You know where this Poisson equation is given in our gate syllabus? Before diode. If you want to really understand the electrical behavior of a PN junction or ISO junction, PP plus junction, NN plus junction, PN junction, P plus N junction, PN plus junction, whatever. The first thing that really is that you have to use in a given junction area is Poisson's equation. Using the Poisson's equation, we determine the junction field at each and every point in the junction, PN junction I'm talking about. Having known the junction field, I will determine the junction contact potential. Later on, I will know the contact potential for a given junction as a function of doping concentrations and the width. I understood what capacitance is. I understood what potential difference of a junction is through Poisson's equation. Ultimately, there is one of the most wonderful, very high-level application of diode called as variable capacitor. You vary the voltage, electronic tuning it is called as. You vary the voltage, capacitance value will change. There are so many places where to tune it to a particular frequency, I should vary the capacitances. That's what we do whenever we tune a radio to a particular station. See the beauty of it. No, I have understood capacitor. I have understood Poisson's equation. I will understand the PN junction electrical behavior completely through Poisson's equation. Apart from that, there is something called a junction capacitance that we call. This particular junction capacitance that I talk about is what we use ultimately when I talk about a variable capacitor. So if I want to understand the primary semiconductor device with only one junction, any other semiconductor devices, multiple junction devices, I need to know Poisson's equation, which is basically given to me by using electromagnetics as a subject. So I will do Poisson's equation here, not in semiconductor devices physics. Ultimately, when I go there, I say, I told you that this is useful here. I will use this. I will calculate this. Next. While talking about the potential only, I will tell you that if the field is conservative, if it is really created by some source, it is not just imaginary given mathematical thing. Total change in potential around a closed path, if I calculate, if it is a conservative field, total change in potential is basically calculated as using E bar dot dl bar. If E bar dot dl bar of a particular field along a closed path is equal to 0, we call it as conservative field. What is this E bar dot dl bar between A and B? It is potential difference. Around a closed path, some of the total change in potential around a closed path is 0, is what we use as KVL in all your network analysis problems. This will ultimately take me towards KVL, because of which I will study this. You know that network analysis requires KCL and KVL. Check it. I'll go through like this. Next. Having defined the potential difference between 2 points, I will apply it to a conductor that has fixed amount of free charge in it. Before applying, I will say when there are free charge is there, I will introduce you to current I. First of all, I will say current is rate flow. Charge in motion constitutes current. Rate of flow of charge through any cross section of the conductor is current. Right? Charge in motion constitutes current. Magnitude value of the current is rate of flow of current. Charge through any cross section. And then I will basically define current as the effect, which is caused by potential difference V. I will take a conductor, I will apply a potential difference, I will calculate the current, I will determine it, I will measure the current by using ammeter. Using voltage and current, voltage across and current through a particular conductor, we will define something called as resistance of a given conductor. I will completely understand what resistance is through electromagnetics only. I will know the formula, or R is equal to, depending upon its dimensions, medium used, the structure of it. It can be cylindrical resistor, it can be resistor of square cross section, it will be a helical resistance, whatever it is, I'm not worried about it. I will be able to tell you, hey, this is the resistance between the terminals of this device. And V is equal to IR is given by electromagnetic fields only to us. Ohm's law. We will derive it. So we will understand resistor, we will understand diode, we will understand capacitor, we will understand current. Ultimately, we will talk about continuity equation of the current. Continuity equation of current is what? In a particular volume, whatever the charge that enters should leave, we'll say. Because charge cannot accumulate at a particular point. No? Any accumulation of charge will increase the force between them and then they repel, go out. Whatever the charge that enters into a particular volume should leave. It cannot get accumulated. It ultimately tells me what? Continuity of current, we call it. Total current entering a closed volume to a closed surface is equal to total current leaving is what? Ultimately, current definitely will come through conductors. So many conductors will carry the current towards the node. So many conductors will take them out, which it ultimately says what? Continuity equation in current I will discuss. Telling that net current entering a particular volume at any point is equal to net current leaving that point. That will ultimately become KCL for me. Charge cannot accumulate at a point. That's all. Leads to something called as KCL. Beyond this, I will use that conductivity, whatever electrical property that we define. And then talk about charge relaxation. And understand that if I somehow put charge into a particular volume, ultimately it will not stay inside the volume, it will come onto the surface. If some charge is put into a particular volume, what is the rate at which it decreases because it distributes is what I will look at as charge relaxation and relaxation time. And this charge relaxation and relaxation time, you should know, among so many theories that are used to talk about something called as gun effect, where you apply just a DC voltage, you get a pulsating current. Excellent, it is actually microwave source, gun diode. Just the DC voltage you apply normally, when you apply DC voltage, you expect the current to be DC. But there is a gun diode as a device which produces pulsating current for a DC applied voltage. That pulsating current is because of charge relaxation. In the devices of negative resistance achieved by creating very high electric field in just silicon wafers. Charge relaxation basically leads to something called as gun effect. Used as microwave oscillator. Normal RC, LC oscillators and all, no, they died on transistor only at so many megahertz will just act as a short circuit. Big challenge it is actually. At very high frequencies, because I want to basically modulate a high frequency carrier, from where I will get it? Very high frequency carriers are to be produced by using very high frequency oscillators. Whenever they are microwave oscillators, basically microwave frequencies, you don't have semiconductor devices which can produce these microwave oscillations. You have to go for microwave devices only. I will understand actually charge relaxation as the basis for. I will briefly talk about this also when I talk about that particular subject. Maybe I will not take many hours for that. I will explain the concept and I will explain whatever is really required for us mathematically and conceptually to go back and go into the different subjects to electromagnetics. Quickly. Maybe 5 more minutes, I'll take 10 more minutes. I'll come to this. Here, magnetic flux, magnetic field we talk about. Then I'll talk about Ampere's law, like Gauss law. And then I will verify this. No, Ampere's law, like Gauss law, is stated first. And then applied. This Ampere's law basically is also Ampere's circuit law because This is used to analyze magnetic circuits. Magnetic circuits are basically transformer circuits, where there is a closed path for magnetic fields for flux lines is actually magnetic circuit. Best example is actually Ampere's transformer. Ampere's law really takes us to something called as circulation, like divergence and curl. Basic application of it, right? Curl is what I look at. Circulation per unit area is what is curl. Using this, I will understand something called as Stokes theorem. When I want to evaluate the line integral of a vector field over a closed path, maybe so many sites, so many different lines, because of which so many different line integrals. So many line integrals around a closed path can be converted into one surface integral, double integral, using Stokes theorem. So line to surface integral. Using Stokes theorem only as a special case, we develop something called as Green's theorem. These are all there in the mathematics part of it. Green's theorem I will use as the basis for the sake of starting complex integration. Without looking at Green's theorem, I will not get into complex integration. Complex integration starts with Green's theorem first, right? Finally, as a fundamental subject, which is not specified in GATE syllabus, final point that I will be talking about is Faraday's law of EMF, induced EMF. Faraday's law is for primary magnetic fields, right? Faraday's law. So all these things ultimately have been defined and use them to really understand the mathematics. So many topics in mathematics. I will consolidate them into finally 4 Maxwell's equations. That is where my syllabus starts. I may take for all these things around 20 to 25 hours. That means in the 20 to 25 hours, I would have completed all vector calculus topics, gradient, divergence, curl, Gauss divergence theorem, Stokes theorem, and ultimately the Green's theorem. While understanding here Faraday's law, ultimately inductor as a component, I will understand. I will derive the inductance of a coil using Faraday's law. Resistance basically ultimately talks about conductance, reciprocal of it, capacitor, inductor, everything is studied through fields. While studying that, we would have really clearly understood so many mathematical topics as well as the topics that is required for our subjects.